Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will continue talking about model selection via hypothesis testing. To be more specific, in this video, we will answer the following question. Does the inclusion of one particular independent variable or predictor variable add significantly to the prediction of y achieved by other independent variables or predictor variables already present in a model? Well, we will answer this question for a particular example. Let's begin. Let me show you the example I would like to discuss with you here. Okay. So if you take a quick look at that slide, you will see that we have talked about that data set before. Okay, but let me quickly remind you. So y in this case represents the number of passengers arriving and departing an airport per airline in a year. And we're trying to predict that variable y, that's going to be our response, using two independent variables or using two predictor variables, which are x sub 1, or let me call it x1, the average number of flights departing per week, and x2 represents the total number of local airline employees. Okay. Our data set looks like that. Okay. So, as usual, let's enter, or let's import our data into R. Let me launch R. So, before we start doing things with R, let me give you an idea of what we're going to be doing next. So first, I'm going to be entering the data, but then I'm going to be fitting two models. First, one that has as the only predictor variable x1, and then we're going to fit a second model that includes both predictor variables, and then we're going to try and construct a test statistic, okay, that can help us measure the contribution of the variable that is going to be added to a model with a single predictor variable. Okay, let's do that. So first, let's enter data. Right, we need y. Okay. So 19.3, 2.8, 30.5, 6.59, 11.7, 6.1, 7.6, 13.4, 50.4, 14.9, 35.4, 6.3. That's it. Okay, x 63 x sub 1 anyway. 63, 21, 94, 50, 42, 21, 36, 48, 104, 49, 89, 25. Second predictor variable, 40, 7, 87, 10, 23, 6, 11, 8, 88, 43, 71, and 8. Okay. Now let me fit, as I said, a model. Let me call it model 1 or dot 1. Okay. So LM, as usual, linear model, where y is going to be our response and our single predictor variable or independent variable will be x1. Okay. Now let's take a look at those coefficients for that model. Okay, so beta had 0, right? Our estimate for the y-intercept is negative 8.69 roughly, and beta 1 hat, right? Our estimate for the slope in this case would be 0.48 roughly. Okay, so the test statistic that we're going to be constructing here will be an f-test. So let me remind you that an f-test is a ratio, right, between two chi-square random variables divided by their respective degrees of freedom. Okay, so to construct this test statistic, this f-test statistic, I'm going to need the sum of squares for error for each of these, the sum of squares of the error for each of these models. Okay, so let me create an object called SSE1, as in the sum of squares for error for the first model, right? So we know that if we want the residuals of a model, right, we have a couple of different ways of finding them, right? One would be this, the name of your model, right, and then just res as in residuals, and then you have those 12 numbers, which are the difference between observed and predicted value. Okay, so what we want to do here is square those guys, and then we want to add them up. Okay, and as I said, let me save SSE for that first model in an object called SSE.1. Okay. So next, let's fit the second model I told you about, one that has not only x1, we're going to be adding the other predictor variable, the other independent variable that we have available. Okay, so we know that's really easy using R. So model number 2 is going to be a linear model that has as its response variable y, but that has two predictor variables, x1 and x2, let's take a look at the coefficients for that model. Okay, now instead of having only 2 betas, now we have 3, right? And let's do something similar to what I did. Let's create another object called sta302, which will contain the sum of squares error for the second model. Okay, let me see what it looks like. Okay, now before we continue, let me remind you that SSE is basically a measure of distance between your observations and your predictions. Okay? Let's compare these two numbers. Let me remind you what SSE 1 looks like, and we have this guy here. Okay? So, as you can see, right, if we fit a model including only the predictor variable x1, our SSE, and again that would be a measure of distance between observations and predictions, is 237 roughly. Okay, when you include the second predictor variable, the second independent variable x2, that decreases, right? Now it's 202. Okay, so the question is, well, yeah, clearly including x2 has helped reduce the sum of squares error, right? Meaning the distance between your observations and your predictions. But the question that we would like to answer is if that reduction is big enough to warrant including that second variable, or in other words, to use the second model instead of the first one, right? So if it's big enough, if the reduction is big enough from a statistical perspective. Okay? Okay. So let's construct the test statistic that is going to help us assess whether or not that reduction is big enough, okay, to justify including x2. Okay, so let's construct that test statistic. So test statistic, so first, as I said, remember that we are going to be using an F test. So we need two components, the numerator and the denominator. Okay, so first let me use the following notation. Okay, so SSE x x sub 1 will denote the error sum of squares when x1, error sum of squares when x1 is the only predictor variable in the model. And well, we're going to have something similar, SSE x1, x2 2 for the error sum of squares when x1 and x and x2 or x sub 2 are included, right? Are both included in the model. Okay. So we said, you know, the reduction in SSE will be given by this SSE x sub 1 minus SSE, well, this guy here, let me copy paste. So the error sum of squares for the model that only includes one variable minus the error sum of squares with the model that includes both predictor variables. Okay. Okay. So, and in this case, we know it's given by 237 roughly minus 202. So if we do the math, right, we do this minus that, so that reduction is 34 roughly. So the question is that reduction big enough to justify including x2? Okay, so it turns out that our numerator will be the reduction in SSE, in the error of sum of squares, right, divided by the number of variables, of predictor variables included in the new model, right, additional ones. So in this case, since it's 1, that's going to be our numerator. Okay, so it's going to be this divided by 1, which is, you know, itself, just to be very explicit. Okay, this is going to be the numerator of the test statistic we are constructing. Let's talk about the denominator. So now the as you can see, the numerator is a measure of the reduction of in SSE, right, for each independent variable included in the new model, if you will. So the denominator is just going to be MSE, the mean square error, but for the model that includes all the independent variables, all the predictor variables. Okay, so let me write that down, that the denominator will be just the mean square error in this case for the model that includes all the predictor variables. And we know that the SSE will be divided by n minus k minus 1, right? Okay, so in this case we have, let me go back to our table, we have 12 observations, so n happens to be 12. K, we have 2 predictor variables that will be included, and well, that's it. So let me write this one down. 202 would be the SSE for the model that includes both. Then we have 12 for the total number of observations. 2 independent variables or predictor variables. That guy will be our MSE. Let's do the math here. So it would be this guy divided by 12 minus 2 minus 1, right? Okay, so roughly 22.5. So now we are ready. Our test statistic. Let me call it F star. Okay, look like this. It's going to be this guy here, the reduction in SSE divided by the mean square error. Okay, and the mean square error of the model that includes all the predictor variables. Okay, so in this case, right, it would be, right, let me type F star will be just this guy here, that reduction, come on. Okay, so let me just copy paste from here. Divided by this, right? So F star is roughly 1.53. Okay? Okay. So we have our test statistic. Well, now that we have our test statistic, you guys remember that a hypothesis test is a 4-step procedure. So the third step would be finding the p-value, for instance. So let's find the p-value. So the p-value, as you know, would be the probability that your F distribution, right, under the null hypothesis is bigger than your F star. Okay? Bigger than F star. Okay? Now, it turns out that under the null hypothesis, right, F star will have an F distribution with 1 degree of freedom for the numerator and n minus k minus 1 degrees of freedom for the denominator. Okay, which makes sense. Okay, now note that we want the probability that an F is greater than some number. Okay, so since we're going to be using R, just keep in mind that what R is going to help you find is the area or the probability to the left of numbers, okay, meaning the CDF. So that's why we're going to be, well, this is less than or equal than this, right, F star. Just to be super specific here. Okay, So let's find it. Again, number of degrees of freedom for numerator 1 clearly, and n minus k minus 1 for the denominator. Okay, so what we want is 1 minus pf, that is the built-in function to find to evaluate the CDF of an F distribution. In this case, we want to evaluate it at f star, which is 1.53 roughly. Degrees of freedom for the numerator 1, degrees of freedom for the denominator n 12, minus k 2 minus 1. Okay, so roughly 24%. Let me use this. Yeah, roughly 24%. Okay. Now, for instance, if our significance level was 5%, right, our conclusion would be, since our p-value is greater than 5%, we fail to reject the null hypothesis, right? Which means that the inclusion of x2 is not such a good idea, right? Okay, so step number 4, conclusion. So since our p-value, which was roughly 24%, so but first let me say, if using alpha significance level 5%, right? So if our significance level were 5%, then since our p-value is greater than 5%, our alpha, right, we fail to reject our null hypothesis H0. And the null hypothesis is that x sub 2 or x2 is not statistically significant. Okay? That x sub 2 is not statistically significant. Okay, or in other words, as I said, including x2 to, well, adding x2 to our model is not going to provide a significant reduction in the error sum of squares. Make sense? In other words, yeah, adding x2 adding x2 to the model that already includes x1 doesn't result in a significant reduction in the SSE. Okay? Okay. Make sense? Well, now let's try and summarize and generalize this procedure. Let's go back to your lecture notes. So, hypothesis tests. A four-step procedure. First step, null hypothesis. So basically what we're doing is comparing two models. A full model that contains, in our case, two predictor variables. In general, we're going to have P for that full or complete model. And X star, right? The other one, the one that we're testing, if it's worth including or not. Okay? Okay? So, the reduced model, okay, is the one that doesn't include X star. Okay? Okay. So, since beta star is the corresponding beta coefficient for this guy, the null hypothesis will be, hey, beta star is equal to 0. Okay, that's a null hypothesis using the beta parameters. Okay, well, beta parameter. Okay, beta star equals 0. Against beta star different from 0. That would be the alternative. Okay. We know that we're going to be using an F test statistic. Okay, we said it's just a ratio between two quantities. This one will have a chi-square with 1 degree of freedom. The one in the denominator, a chi-square with n minus k minus 1 degrees of freedom. The one on top, right, measures the reduction in SSE, right? And this one is just mean square error for the complete model. Okay, the one that includes all p variables and X star. Okay, in our case it was, you know, just the one that included two predictor variables. Okay, the as we said, the distribution of the test statistic is going to be an F distribution with 1 degrees of freedom for the numerator, n minus, in this case we're using p, right, for the number of variables that are already included plus the candidate X star here. Okay, so anyway, in this case, using that notation, right, the denominator will have degrees of freedom n minus p minus 2. Okay. And well, it turns out that there's an alternative. Okay, the alternative, and just okay, and the alternative would be using a t test. So remember that an F is chi-square divided by its degrees of freedom, and divided by chi-square divided by its own degrees of freedom, right? And remember that we only have 1 degree of freedom here. That's a chi-square in the numerator. That's a chi-square with 1 degree of freedom. So, on the other hand, t distribution is a normal 0, 1 divided by the square root of a chi-square divided by its own degrees of freedom. If you square a normal 0, 1, you end up with a chi-square with 1 degree of freedom. If you square, square root, you end up with a chi-square divided by its degrees of freedom. So anyway, just a reminder that t square is going to give you, t square has an F distribution. Okay, so we will see that in this case, when you want to just test what happens if you include an additional predictor variable, right, you can use either one of them, an F test or a t test. Okay, so using a t-test, null hypothesis, beta star equals 0, just like before, right, against the alternative that beta star is different from 0. So t-test, let me use that notation. What we're going to have is an estimate of beta star divided by a standard error of beta star. Okay, and as we said, well, we can show, it can be shown that there's a correspondence between our F test and this T test. Okay, let me show you in this particular case. Remember that we had here a model 2, right? Mod 2, this guy here. Okay, so if we just type summary of model 2, we should get that output that I'm showing you here. Okay, okay. Now let me use that output from the slide. Okay, so what we said is our T star is going to be an estimate divided by the standard error. Okay, so this is beta hat star, this is the standard error of beta hat star. Let me do that. This guy divided by this guy, that's my T star. Okay, can you see that you have it here? That's your T star. So that's T star, or test statistic. And then what we want is the p-value, right? And remember that the p-value, because in this case it would be a two-sided alternative. Beta, and the null hypothesis is beta star equals 0. The alternative hypothesis is beta star is different from 0. So the thing is, what you would like to do is something like this, right? 1 minus probability that well, minus the CDF evaluated at T star, right? And the degrees of freedom, right, are going to be n minus k minus 1, meaning 12 minus 2 minus 1 in this case, right? Okay, so here we go. But is that what we want? No. The thing is that that would be for a one-sided alternative. So remember that the expression of the p-value looks something like this. The probability that t distribution is greater or equal to, anyway, the equal is not going to make a difference, than the absolute value of this guy, but actually you multiply by 2. That's expression for the p-value when you have a two-sided alternative, right? Okay, so what we want to do here is this guy multiplied by 2, right? Now can you see that you end up with this guy here? This is the p-value, okay? And something else, remember our p-value from before, right? If we go back to what we did here, 24.65%, right? Okay. Something else, we said, well, if you square T star, you should have your F, right? That's 1.5359, right? So up to round of error, that's what we have, right? Okay. Anyway, I just wanted you to see that, okay? So you have two options when you're doing this sort of analysis, when you want to assess how appropriate is the inclusion of an additional predictor variable to your model. Okay, so basically what we said here. Okay, so anyway, let's summarize. What we did here together was answering the following question. Right? We came up with a hypothesis test for the addition of a single variable. We wanted to see whether or not it was reasonable, it was a good idea to include another predictor variable to a model that already includes some other independent variables. And the way to assess how useful could be that new predictor variable is by using a hypothesis test. And that hypothesis test could be carried out using a test statistic with an F distribution or a test statistic with a T distribution. Okay, but in the end they are equivalent. Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.